In the next section of Chapter 12, we want to look at particular properties of intermolecular forces in liquids and solids, including evaporation, condensation, melting, freezing, and sublimation. Looking at the first two, evaporation and condensation, and the effect that thermal energy has on those, the effect of heat on those, we say that the rate of vaporization, the rate at which liquid goes into the gaseous phase, the vapor phase, will increase with increased surface area. So you know if you want something to evaporate quicker, you spread it out so it has a higher surface area, and also an increase in temperature. So if you heat it up more, it will evaporate faster. Water will boil faster. There is a decreasing strength of the intermolecular forces in that substance. And when we look at liquids as a whole, if we have liquids that evaporate easily, we say that those are volatile liquids. Ones that do not vaporize easily would, of course, be called non-volatile liquids. So looking at a molecular view of evaporation, if we look at the molecules that are on the surface of the liquid, we know that they see less overall intermolecular forces. We already looked at the idea of surface tension, so there are forces drawing down on those top molecules, but there's nothing above them holding them together. So because they're held less tightly than the ones that are on the interior of the liquid, then the most energetic among those surface molecules can break away into the gas state. And that is what evaporation is. It's putting enough energy into those surface molecules to allow them to go from liquid to gas. So if we're talking about evaporation or vaporization, a substance is converted from liquid to gas. Now, of course, we can view that in different ways, and the math has to come into it somewhere. We're going to look at some math in this. At a given temperature, if you have a sample of molecules or atoms, there's going to be a distribution of their energies. Not every molecule in that substance is going to have the same kinetic energy. And there's only a small fraction of those molecules that have enough of that kinetic energy to escape from the liquid. So if we look, this is the fraction of molecules right here that have enough energy to make that escape. So we have to get past this critical temperature point right here. Now, we'll look at the math in a minute on that, but let's talk about the other states first. Evaporation and condensation. Let's go in the opposite direction. Condensation is the physical change from something in its gaseous state to its liquid state. So evaporation and condensation are opposites. Evaporation is going from liquid to gas, condensation, gas to a liquid. Now, at some point, the rate at which these are occurring becomes equal. So the number of gas molecules that are condensing down into a liquid is equal to the number of liquid molecules that are escaping and becoming a gas. When you reach that point, you have reached what is known as dynamic equilibrium. At this point, the number of gaseous molecules above a liquid remains constant. And it doesn't mean that those same molecules are going to stay as a gas, but it means for every one molecule that goes from a gas into a liquid, another molecule is going to gain that energy and kick out from the liquid into the gas phase. And once we've reached dynamic equilibrium, this is then translated as the vapor pressure of the liquid. Okay, the vapor pressure of the liquid is the partial pressure of the vapor when it is in dynamic equilibrium with the liquid. So vapor pressure becomes very important to us in certain applications. Again, a molecular or visual look at this. If we put some water into a flask and we cap it so that now keep in mind, to reach dynamic equilibrium, there needs to be a fixed volume for that gas. Otherwise, the molecules are just going to continue moving away and they're from the liquid and they're going to escape. So in this case, when we have the sealed container, evaporation starts to occur, and we start to see just a little bit of fogginess on the inside. We see some steam building up. Okay, evaporation continues, but now, once we reach a critical mass of gas molecules in here, then they begin to lose enough energy that they can't stay in the gas state, and they begin to condense back down. And so we get this equilibrium, this cycling of these molecules, until we finally reach dynamic equilibrium. In dynamic equilibrium, these two rates, evaporation and condensation, are equal to one another. Okay? It's a one-to-one molecular switch as they're going through that. Now, vapor pressure will be constant for a given set of conditions once you have a particular pressure and temperature set up there. But you can change vapor pressure. If you increase the temperature, for example, if you make it hotter, you're going to put more energy into those liquid molecules. You're going to get more of them in a vapor. Or if you do something to decrease the strength of the intermolecular forces that are in the liquid. Now, vapor pressure is not dependent upon the surface area. We did say that if we increase surface area, we increase evaporation, but it doesn't affect vapor pressure, because if we increase the surface area at equilibrium, we're going to equally affect the rates of both evaporation and condensation. So it's a two-way street there. So surface area doesn't affect just one side of the equation, it affects both sides, and they kind of cancel one another out. Now, if we look at boiling, what happens when we boil a liquid? Well, during boiling, we're pouring thermal energy into that water until eventually we have enough thermal energy to make the water molecules on the inside of the liquid so it's not just the ones from the surface. The ones in the center gain enough energy to become gaseous. But the problem is they're a gas trapped under a layer of liquid, so they form a gas bubble. Now, that gas bubble, we think of it as just being air. It's really not air. It's full of gaseous water molecules. So that's why as those bubbles come up, they are released as steam, and there's a lot of steam over the top of that boiling water. So what we can do then is look at these phase changes, and we can use it to develop what we call a heating curve for phase change and for the change in temperature. So looking at a boiling liquid, water in particular, once you reach the boiling point of a liquid, then it doesn't really help to pour more heat into it as far as, reaching that point. You've reached the boiling point. So all it's going to do when you add heat to it is cause more rapid boiling. You're just pouring more energy into it. Those molecules, once they're boiling, are going to go from liquid to gas state. It's just how quickly they do that. What you cannot do is really raise the temperature of the liquid above the boiling point. A liquid is only going to reach a certain temperature under a given set of conditions. So for example, if we have a mixture of boiling water and steam, the temperature of the boiling water and the steam are going to be 100 degrees Celsius, assuming we have 1 atmosphere of pressure. And the only way you're going to get that to increase in temperature is to convert all the water to steam. Until all the water has become steam, the temperature is going to stay at 100 degrees Celsius. Once you get it all into the steam form, again, if you hold it at the particular pressure you're at, then you can get the temperature of the steam to go higher than 100 degrees Celsius, but not until you've completed that phase change. At that point, all the energy is just going into that conversion from liquid to gas. So what we can do is represent that as what we call a heating curve. And that is just plotting a temperature in degrees Celsius versus the amount of heat that you're adding to a system. So the temperature of the water, as it's heated from room temperature, so we're assuming room temperature is down around 20 degrees Celsius, and we're going to start adding heat to it until it gets to 100 degrees Celsius. Now notice this part of the curve, what's happening when we do that. What it's doing is causing the temperature of the liquid to increase. So that heat that we're adding in is simply going to making the molecules in the water move faster. Now, once we reach 100 degrees Celsius, if we look right here, we're going to continue adding heat, but notice the temperature does not change from this point to about this point. We've added this much heat without changing the temperature. It stayed at 100 degrees Celsius. So that flat line on a heating curve is telling us we're undergoing a phase change. No temperature change is occurring, so it must be a change of phase. Okay. Temperature is going to remain constant as the liquid begins boiling. So at this point, over here in the first case, temperature of the liquid increases. All I'm doing is making hot water. I don't have any gas at that point. Once I reach 100 degrees, I start to produce gas. Okay? And so all the energy is just going into converting liquid molecules to gas molecules. That's all that's happening. Now, in the last part of the graph, if we look at that one, suddenly we reach a point where now adding heat starts to cause the temperature to rise again. Okay, now at this point, everything is a gas, and what we're doing is increasing the temperature of the gas from 100 degrees up to whatever point, in most cases about 135 degrees, 140 degrees. Okay? So heating curves can be very useful to us in the interpretation of what a substance is doing, what phase it's in, what it's undergoing. So when we look at that, we need to think back to our definitions of endothermic and exothermic. We come back to those on a fairly frequent basis. Now, if we look at evaporation, this is it's an endothermic process. So in order for a liquid to go from a liquid state to a gas state, it has to absorb energy as heat. That is what's required to break those molecules away from the other molecules, to overcome those intermolecular forces. They have to become energetic enough to move quickly and become a gas. So we don't think of it that way. We think of, oh, well, it's getting hot. We think of it as exothermic, but the heat is going into the system. So remember, the system absorbs heat, that's endothermic. Now, our bodies take advantage of the endothermic nature of the evaporation process to cool ourselves off. So what happens is we overheat, we sweat, we get this layer of water on our skin, lots of surface area, and it starts to evaporate, okay? Because all of the energy that is in our body as heat is now being poured into this liquid water, high surface area, and then as those molecules go from liquid state to gas state, they carry that energy with them. Okay? So the water evaporation absorbs heat from our body and we cool down. Now you'll notice people talk about being somewhere where it's hot and, oh, well, it's not too bad because it's a dry heat. Or if you've ever been in the deep south in the middle of the summer, you know that it's really miserable and people talk about it being like a sauna. High humidity will slow down the evaporation rate because the air already contains lots of water vapor as humidity. And so it's harder to reach that vapor pressure point. So sweat doesn't evaporate very quickly. It just kind of sits on your skin, holding all that heat in, and you stay kind of hot and sticky, and you don't cool down as quickly. So that's why areas where we say, that have low humidity, we say it's a dry heat. You don't feel as hot because you're taking advantage of evaporative cooling much more efficiently. Now, if we look at condensation, we said it's the opposite of evaporation. So if it's the opposite, it's going to use the opposite thermal, which is exothermic. So to condense, a gas has to release its heat to the surroundings to become a liquid. So for instance, steam. If you ever have accidentally got your hand over a pot of boiling water, the steam will condense onto your skin because it's going from higher energy in the steam to lower energy in your hand. It's going to convert that energy to you. So as it releases that heat, it can burn your skin. So you can put your hand in an oven That's 350 degrees. Air doesn't transmit heat very well, and so really, you could put your hand in there for a few seconds and it wouldn't do anything to you. 350 degrees Fahrenheit. But if you think about water, 212 degrees Fahrenheit, 100 degrees Celsius, if you put your hand over that boiling water, it's going to burn you very quickly because the water transfers that heat very quickly. Now, condensation being exothermic is also why, if you look at the winter overnight temperatures in coastal cities, they don't get as low as you see in a desert, which may sound odd, but deserts are, again, they're very extreme. They're very, very hot during the day, but they tend to get very, very cold at night because they have dry air. Coastal cities are picking up a lot of water vapor from oceans and breezes coming in off the oceans, and so they don't have as big an exchange rate there. So water will condense out of the air in a coastal city, releases heat, keeps temperature from dropping. But in the desert, there's no moisture in the air to really condense, so the temperature can just keep dropping. There's no exothermic reaction to take advantage of. Now, when we talk about these heats or energies, of course, we want to be able to quantify that. We want to be able to measure that. How much energy does it take to boil a pot of water? Or how much energy does it take to raise the temperature of the water from room temperature to boiling? We can look at that in terms of different heats. The first one we'll look at is the heat of vaporization. And the heat of vaporization is the amount of heat that it takes to vaporize 1 mole of a liquid. So 1 mole of liquid going from liquid to gas. If we look at water in particular, heat of vaporization is different for every liquid. Water is the classic one, so that's the one that we'll do all of our calculations with. We'll look at that one as our example here, but be aware you could do this with any liquid. You just need to know what those values are. What is the heat of vaporization for the liquid you're looking at? The heat of vaporization of water at normal boiling point, which is 100 degrees Celsius, is 40.7 kilojoules per mole. Now, again, don't worry about memorizing that number. That would be a value that is given to you, but we want to look at how we can use that value to do some calculations. We'll get there in a few slides. Now, notice that it's a positive number. Heat of vaporization is positive because vaporization is endothermic. So remember, when we look at energies, if it is endothermic, it's a positive number. That means heat's being absorbed. If it is a negative number, that's the amount of heat being released. That would indicate exothermic. So the same amount of heat would be involved going from gas to liquid when gas condenses, but heat's emitted rather than absorbed. So heat of vaporization would be, the heat of condensation. Okay, heat of vaporization is negative going from gas to liquid. Okay, so here, heat of vaporization, this is liquid to gas, and this really should say condensation. Okay, and I'll just abbreviate CON here. They're using the same one. It's, if you see it as negative, if they ever say heat of vaporization, they leave it that way, and you see it as a negative 40.7 kilojoules per mole, that is telling you that they're talking about the condensation process. So you may see it both ways. I like to use heat of condensation to define the difference between those, but really the sign is what tells you which way you're going, positive or negative. So if we look at heat of vaporization of water, okay, in this case, liquid to gas, positive value, gas to liquid, negative value. Okay, so pay attention to those signs. They become very critical when you're doing these types of calculations. Now in your book you have a table that shows some of the common heats of vaporization for a variety of common liquids: water, rubbing alcohol, acetone, and diethyl ether. And you can see, again, formulas. You'll see their normal boiling points. That's at room temperature, 1 atmosphere of pressure. Here are these heats of vaporization. So again, this is always going from liquid to gas, these positive values. If you're going from gas to liquid, make them negative. Okay. And now that's at their boiling point. What is the heat of vaporization at room temperature? It's actually a different value. So you have to pay attention to, are we at the point where we need to go from liquid to gas, or do we have to pump a little bit of energy in there, such as at 25 degrees Celsius, to get it up to the boiling point first? And you can see how those values differ slightly. They're a little bit higher. So you would use the heat of vaporization of a liquid to calculate the amount of heat energy you need to vaporize some given amount of that liquid based on a number of moles of that liquid. And you can use the heat of vaporization as a conversion factor. Okay? So how do we use it as a conversion factor? Let's say that we want to determine the amount of water in grams that we can vaporize at the boiling point of water. So it's at the boiling point, so that's the first column of numbers that was in that table. And we want to use 155 kilojoules of heat. So we're given how many kilojoules of heat we have. We're trying to figure out how much water we can vaporize with that. The one thing that they don't tell us that we have to look up from that table is the heat of vaporization for water at the boiling point. And if we look that up, that's the one we talked about. It's 40.7 kilojoules per mole. And we are vaporizing, so going from liquid to gas, so it's a positive value. That's going to have to be absorbed. So to get from kilojoules of energy to the number of moles, we know this is the number of kilojoules for every 1 mole. So if we carry out this step, we know how many moles of water we have. Well, we don't want moles, we want mass of water, so we need the molar mass of water. So if we look that up in the periodic table and add it up, 18.02 grams of water for every 1 mole. So we find out that 155 kilojoules of heat can vaporize 68.6 grams of water, which there's about 1 gram in a milliliter of water, so about 68.6 milliliters of water. That's not too shabby. Now we can also look at other phase changes. So going to the solid ends of things, what if we look at the processes of melting and freezing, going from solid to liquid or liquid to solid? So the thermal energy that we pump into a solid causes the molecules and atoms to move and vibrate faster until they eventually have enough thermal energy to overcome, again, stronger intermolecular forces, and those molecules can start to slip and slide over each other. Solid will turn into a liquid at the melting point. Now these are all things at this point that you're probably familiar with the terms and the basic idea, but you want to think about them on a molecular level. What's going on with the molecules when these things happen? When ice melts, the water molecules are breaking free from their solid structure. They're moving out into a liquid form. Now when we have a mixture of both ice and water, the temperature will go down to 0 degrees Celsius, and all other things being equal, if you're not putting salt in there, colligative properties, we're not changing any of that. The temperature is going to remain at 0 degrees Celsius for an ice-water mixture as long as you have ice present at 1 atmosphere of pressure again. Now, once all the ice melts, if you continue heating that water, now what you're going to do is start raising the temperature of the liquid water past 0 degrees Celsius. So if we look at our heating curve, it looks very, very similar to the one we saw for the boiling or vaporization process. But the only thing that changes really are the temperatures. So again, notice we've got, from this minus 20 degrees, so we have ice that's very, very cold at minus 20 degrees. We pump heat into it, and the temperature increases with heat until we reach 0 degrees. Now from 0 degrees all the way across here, notice we add a lot of heat to it, but it doesn't change the temperature. This whole range in here, we have an ice-water mixture. There is ice and water present over that whole line until eventually all the ice melts, and now energy that gets pumped into it can go to, again, increasing the temperature. So we start to see it go up again. So we want to be able to look at these heating curves and interpret them in terms of what's going on. Now, looking at the energetics of melting and freezing, we know that if we want to cool down a drink, we drop some ice cubes in there. What's happening is, as the ice melts, the drink's getting cooler because the melting process is endothermic. The energy from the liquid in the glass is being absorbed by that solid ice to convert it to a liquid. The melting ice is just going to keep absorbing heat from the liquid until the liquid and the ice reach the same temperature, until they get down to 0 degrees. Or, if there's enough ice in there, or until the ice runs out of energy to absorb from the water. Now, melting is an endothermic process. Freezing is exothermic. If you stop and think about it, it's very similar to what we looked at before, so it should make sense. We have to put energy into an ice cube to melt it, so it absorbs it, endothermic. Freezing, we have to get the energy out of the water to get it to go into the solid form, exothermic. So when you're putting an ice tray in the freezer, or if your automatic ice maker is making ice, it's carrying out an exothermic reaction. You have to pump heat out of that. That's why you can't cool your house with a refrigerator if you just open the door, because what it has to do is remove the heat from an area to get it to cool down. So you'll notice the area around your refrigerator is actually quite a bit warmer because it's pulling all the energy out of the inside of the box and translating it to the outside air. Okay. So a refrigeration system has to remove heat from that interior, otherwise heat released would warm the freezer when you put ice trays in, and it wouldn't freeze any longer. So heat of vaporization is liquid to gas state. Going from solid to liquid state and vice versa is known as heat of fusion. So the amount of heat required to melt 1 mole of a solid to go from solid to liquid is the heat of fusion. For water, that is 6.02 kilojoules per mole. Heat of fusion, going from solid to liquid, is positive, endothermic. If we are going to go from liquid to solid and freeze it, heat's going to be emitted. So in that case, the heat of fusion becomes negative. So if it's a positive number, then you're melting something. If it is a negative number, you're freezing it. Again, we have our equations, so we can see solid to liquid, positive number, liquid to solid, negative number. Okay, so just keep that in mind on those. Again, the numerical value, don't try to memorize those. That would be in a table where you could look that up. But we can use this to carry out our calculations again. We want to use the heat of fusion to calculate how much heat it takes to melt a given amount of a solid, such as a piece of ice. So we can use the heat of fusion as our conversion factor to get from energy to moles of the solid, from moles to mass, or vice versa. In this case, we want to know how much ice we can melt if we have 237 kilojoules of heat. So I start with 237 kilojoules of heat. I'm trying to find the mass of water that I can melt here. I need the heat of fusion. Okay. Now, since I am going from solid to liquid, I know it's going to be a positive value. And I looked that up in my table, so for every 1 mole it's 6.02 kilojoules, and again, it's the exact same equation we looked at before. We need molar mass of water to get from moles to grams. So the only thing that's changed here, I have a different amount of energy. They gave me a different number of kilojoules, and I have a different number. Heat of fusion is different from heat of vaporization. The setup's the same, the number's a little different. And so now I find out that I can melt 709 grams of ice using 237 kilojoules of energy. And notice that this number is much larger because heat of fusion is smaller than heat of vaporization. It only took 6.02 kilojoules of energy for every 1 mole of water to go from solid to liquid, but I needed 40, more than 40 kilojoules per gram to go from liquid to gas. So a little bit more energy getting into that gaseous state there. Now, we looked at 2 individual heating curves for the heat of fusion and the heat of vaporization, but keep in mind, there's nothing saying we have to break those into two graphs. We can put them all together and create a heating curve for a substance over its entire range. So for example, what you're seeing here is the heating curve for ice from a very cold piece of ice, or heating curve for water in general. So we're going from a very cold piece of ice at negative 25 degrees all the way up to gas, to water vapor at 125 degrees. Okay, so here's the difference here. And we've got the same chart. We're going to add heat this way. We're going to increase temperature this way. So what we see is that we pump energy in until we hit zero. So all of that energy just went into warming up the ice to the melting point. Now we hit a flat line right here. All of that energy is just going from converting the ice into water. So this is our ice-water mix here. Okay, and now we've got all water. We start pumping in energy all the way up to here, and we are warming up the water to get it to the boiling point. Now we've got this big long flat line here, all the energy that gets pumped into the water to convert it to gas. Finally, we reach a point where we have nothing but gas. Now we can start to heat up the gas. So if we look at this, if we look at the sections that are labeled here, sections 1, 2, and 3, we want to correlate those with the correct state of water. So what state would you have at point 1? Well, we're on a flat line, so that's telling us flat line is a phase change. That means we have two phases present. We have, in this case, both solid and liquid water present at that stage. Now, if we look at 2, okay, we're on an uphill curve. It is not a flat line, so there's only going to be one phase when we're on an uphill, when the phase is changing, or where the energy, heat added, is changing the temperature. So when the temperature is increasing, here going from 0 to 100, that's liquid. Okay, so here we had solid plus liquid. Here we have just liquid. Okay, and then state 3, this is where we're pumping in energy, getting from liquid to gas. So we have both phases at point 3. Now, if we made a point 4 right here on this one, this would be just gas. So you can use that curve to interpret what stage you're at for any of these points. Now there is one other special case we want to look at, and that's sublimation. Sublimation is something you're probably familiar with, even if you don't know the term. It's a physical change in which a substance goes from its solid state directly to the gaseous state. It's kind of a special state. And when a substance does this, we say it sublimes. And when it does, the molecules leave the surface of the solid as a gas. They just skip right over the liquid phase. Things that do this that you're familiar with, one of them is one that's kind of fun to play with if you've never played with it. It's dry ice. That's solid carbon dioxide. Now, if you've ever played with a piece of dry ice or seen it, you'll know that if you lay it out, it just starts getting smaller and smaller and smaller until eventually it disappears. There's never a puddle of liquid under it. It doesn't melt at any temperature under straight atmospheric pressure. If you want to make a liquid out of carbon dioxide, you have to put it under pressure. Now, when carbon dioxide becomes a solid, this occurs at negative 78 degrees Celsius. It's very, very cold. Once you get to negative 78 degrees Celsius or warmer, there's enough energy in those CO2 molecules for them just to skip off straight into the gaseous state. So when they do, they usually condense the water vapor around them, and you'll see these kind of the steam or smoke coming off of it. So just be aware. A lot of people think that the fog that they see over dry ice is the dry ice going into the gaseous state that you can see it. There is some carbon dioxide in there that you're seeing, but mostly what you're seeing is where it's condensing water vapor in the air. You'll notice you don't see nearly as much fog when the air is really dry, or it's dry around the dry ice, as opposed to when there's water. So for instance, if you put a piece of dry ice into a container of water, you'll get a lot of fog, and it really truly is fog. It's condensed water vapor. You're making your own cloud doing that. Now, other things that will sublime. Ice, regular ice made out of water. It will slowly sublime when you have temperatures below 0 degrees Celsius. So if you have a very cold climate, if you have permafrost or something like that, ice or snow that lays on the ground will gradually disappear, even if the temperature stays below 0 degrees Celsius. It's not melting, it's sublimating. So you may have seen the same thing in your freezer if you use old-fashioned ice trays, or if you have ice cubes that get in the bottom of your automatic, of the tray of the automatic ice maker. If they get left in there a long time, you'll notice the cubes at the bottom are smaller than the ones at the top, and they kind of start to stick together. Well, what's happening is those ice cubes are sublimating in that area in the freezer. Another place you can see sublimation is when ice sublimes out of frozen food. So if you take out a bag of food that's been frozen for a long time in one of those airtight plastic bags, you'll see that when you open it, there's a lot of ice crystals in the bag. Where did that come from? Did they, leave these things wet and put them in there? Well, not really, but most food that you're freezing has water in it. And so what happens is the ice crystals in the bag are water that's sublimed out of the food, and then because they were in a closed container, they hit the walls of that container, lost energy, and then redeposited it as ice on the surface of the bag. And so if you open a bag of food like that where there's a lot of ice crystals, you'll notice that the food that's in there seems kind of dried out and unappealing, and we call that freezer burn. It's not really burn, it's kind of, dried out food. So you can avoid this by keeping foods colder than 0 degrees Celsius. So you put them in what's known as deep freeze, so that they're not at that point where they can sort of sublimate. Now, the colder the temperature, the lower the rate of sublimation. So some sublimation is going to occur, at temperatures below 0 degrees Celsius, but the colder they are, the slower it happens. So the food stays good longer. And then I'll mention one other thing that your book doesn't mention that you may be familiar with as sublimating, and that's mothballs. If you've ever been around mothballs or known anybody that's used them, you buy them and they come in this little solid state. They're these kind of smelly things that are designed to keep moths out of your closets, out of your clothes, whatever, and you roll them into your closet, you put them in your chest of drawers, or you roll them under the couch, and then you just leave them there. Well, you can definitely smell that they're there, but if you ever go back looking for them, after a certain period of time, they've disappeared. What happened to them? Well, did a mouse get in and carry them away? Where did they go? Well, they sublimated. That's what it's designed to do. Mothballs are made out of, they used to be made out of naphthalene, and now they're naphthalene, paradichlorobenzene. They're pretty nasty things. They're not things that you want to be breathing a lot of, but that's what's going to happen. If you use a mothball, it sublimates away, goes from solid to gas, and then that gaseous chemical is in your house, and you can smell it. They have a very distinct odor, and then you're breathing that in. So it's kind of discouraged to use mothballs in areas where people are going to be a lot and going to be breathing the air. It's okay for storage as long as you realize you're going to have to air out whatever you're putting in storage after a time to kind of get rid of that smell. Anyway, those are some of the properties, and looking at heats of vaporization, heats of fusion, a few calculations with that. In the last part of Chapter 12, we will take a closer look at this idea of intermolecular forces. We've been talking about the properties caused by intermolecular forces, but we want to look at what are these intermolecular forces and how do we kind of predict what types of intermolecular forces a material would have.